Hi everyone, good morning, good afternoon, or good evening depending on where you are. Special thanks for the folks in the West Coast for your motivation to wake up super early to watch my talk. Okay, the tale I'm about to tell you, like many frightening or dreadful stories, starts with a tweet. I was a fresh, young and optimistic PhD student working on a paper that we published last year at PETS that required me to look at some variants of the original differential privacy definition. So I started a small literature review to find out what was out there. I found more definitions than I expected. Many of them were not easy to understand, let alone compare with each other. So I did the mature, adult thing, and I posted a snarky tweet about it. I forgot about the tweets, but a couple of months later, I received an email from another PhD student, Balazs Peyo, who was going through pretty much the same hurdles as I was. So we compared lists, and we realized that we both were missing more than a few definitions, and we commiserate. The existing literature is a mess. Why is this hard? These are just definitions. It shouldn't be difficult for a newcomer to the field to know what's out there. You know what they say, right? Be the change you want to see in your academic community. So we decided to do this in a more systematic manner. At worst, having a single list of everything out there in terms of data privacy definition would be useful. At best, we might be able to get new insights, group similar definitions together, and simplify the overview of the field. Okay, can someone guess how many definitions we found? Oh yeah, right. That's a recording. The answer is, we found a lot. More than we expected. And the trend doesn't seem to be slowing down really either. So something must lead people to keep creating new variants. What is it, and how can we put some order into this gigantic mess? Let's take the first example and reintroduce the original definition of differential privacy. In differential privacy, you take two data sets, D1 and D2, that differ in the data of one single user, and you say that your mechanism M, any kind of outputs, any kind of events that the mechanism will output when used on D1 and D2 will happen on both D1 and D2 with a similar probability, up to a multiplicative factor of e to the epsilon. So in the original definition, D1 and D2 differ in one user. And it means that based on the output, you can't find out which one between D1 and D2 we picked initially. So what if we change this neighborhood definition into, for example, a group of 5 users? We obtain something that's called 5 epsilon group privacy. This is the definition is stronger, right? If instead of protecting a single person, we're protecting whole groups. We can also imagine weaker definitions, where what is being protected is a single attribute. For example, in a medical data set, you might be able to protect the diagnostic information, but not the demographic information of a patient. So, what is the intuition behind this? The intuition behind this is that these variants are changing the protected property. The thing that is being changed, that is being changed between D1 and D2. So, if the attacker cannot distinguish between D1 and D2, the difference between D1 and D2 is what is being protected, right? So, changing the neighborhood definition changes the unit of privacy, if you will. What does the definition protect? This is one way of changing the differential privacy definition, an easy one. Let's look at another thing you can do to change the definition. Here's a rewritten version of differential privacy. For any possible output O, the privacy loss associated to output O, the log of the ratio between the probabilities of obtaining these outputs for D1 or D2, is always lower than epsilon. Intuitively, that privacy loss quantifies how much probabilistic information the attacker gains. Here we see that differential privacy is a worst case property. You have to consider the event O to find epsilon that has the largest privacy loss, the largest epsilon, if you will, even if it's really rare. Differential privacy is really a worst case property. Instead of doing that, you could instead consider the privacy loss except on its extreme values. So you're allowing larger privacy losses than epsilon, but only with probability, let's say delta. That might be, let's say, tiny, 1 to 1 billion or something. That's called epsilon delta probabilistic privacy, which is slightly different, it turns out, from epsilon delta, the differential privacy, also called approximate differential privacy. It's slightly different, but it goes in the same direction. The idea is to allow for very bad events to happen with low probability. Or, instead of doing that, because even like arbitrarily bad events, even with small probability, are scary, you could do what insurance companies do, and you could weigh the risk of each possible output according to its probability, essentially averaging the privacy loss. It's not super obvious, but this is actually what alpha epsilon Rényi differential privacy is doing, if you have heard of that thing. Okay, what else can we do on the definition of differential privacy? And more importantly, how do we classify definitions in those along those axes? So, that first example changes the risk model, right? Instead of considering the worst case property, we consider the almost worst case or the average case. So this is changing the risk model, is what these sort of group of definitions are doing. So the first natural approach is to classify definitions in categories, depending on how they change the original definition. For each one, you just put them in the nice bucket that corresponds to that change. We quickly realized that this wouldn't work. The problem is that a number of variants, they do multiple changes to the original definition. So they don't clearly belong in one category or the other. Instead, we use the concept of the dimensions. Dimensions are ways you can change the original definition. They have two characteristics. The first one is that you can combine two variants, the second one from different dimensions. The second one is you cannot combine two variants from the same dimension. So let's take an example. Here we have two dimensions. Let's say A is the risk model and B is the neighborhood definition. You have one variant in each dimensions. You can combine those to form a new definition. It's possible. The new definition is sensical. It makes sense. That's mutual compatibility. However, if you have another variant in dimension B, for example, like group privacy on one hand and attribute privacy on the other hand, then you can't combine these two. You have to choose, right? You can't combine B1 and B2, but you can very well combine A1 and B2. Okay? We mentioned two of these dimensions already. We found 7 in total. So to give a human-speak version of these dimensions, here is a quite verbose formulation of the guarantee that's offered by differential privacy. An attacker who has perfect background knowledge, except on their target, and unbounded computation power, is unable to distinguish anything about an individual, uniformly across users, even in the worst case scenario. So we don't think of all of these properties when we think about differential privacy intuitively, but this is sort of really what it corresponds to. So there are already two parts that we saw before how we could change, right? By changing the definition of neighborhood, we change what is protected. By relaxing the worst case property, we change the risk model. What else can we change? We identified 5 other aspects, and now we're going to take a look at them. A quick look at them. Don't worry. Okay. We already saw the first 2. So some definitions give different privacy guarantees to different people in the database, saying that, say, essentially more people get more privacy, lower epsilon, than others. So the privacy loss is allowed to vary across inputs, typically to model users with different privacy requirements. Some definitions assume that the attacker has some uncertainty over the original datasets, and they take this uncertainty into account when quantifying privacy guarantees. They assume that they maybe know only half of the record in the original database instead of all of the record except their target. Some definition change the formalism used to define the attacker's success, rather than this privacy loss that we saw earlier. For example, this is like some definitions use the total variation distance as a first-class citizen, or hypothesis testing as a first-class citizen. Rather than saying, okay, we're using indistinguishability in the definition to say, like, the attacker cannot gain more information about this specific property, some definitions capture the idea that the mechanism does not leak more information than another mechanism. Essentially, we have a list of things, a list of functions that we consider safe, and we say this mechanism does not leak more than these. Finally, some definitions relax the implicit assumption that the attacker has infinite computational resources. This is typically done to combine cryptographic techniques with differential privacy. Okay, so I could dig into each category. We became a little bit of a pair of nerds on privacy definitions. So we could definitely dig into those, present more definitions, go on forever about interesting things we found, etc. But I'm thinking this is not going to be the most exciting presentation. So rather, I'm going to tell you about the challenges we encountered. First, because adversity is fun. And second, because we suspect that these are kind of typical problems that you encounter when you work on a survey paper like we did. The first problem is that scoping is hard. Once we decided that we wanted to exhaustively list definitions, there's an obvious question here, which is, what are we listing anyway? What is the criteria? What is the scope here, right? Initially, we were very optimistic. We said we were going to list privacy definitions. Then we quickly realized that we needed to restrain ourselves to data privacy definitions, because there are many other completely different fields that have completely different definitions that don't apply at all to what we wanted to do. And we actually ended up limiting ourselves to only differential privacy variants and extensions, because there are many definitions out there that are kind of impossible to compare because they're just doing things completely differently, and generally they don't provide any formal guarantees on what an attacker can get or not get. Second question is, okay, now that we have the list of definitions, what do we say about them? Listing them and maybe giving some intuition is kind of nice, but what's even nicer is comparing them. So we summarize results about the relative strength of definitions. For example, this definition implies this other definition, possibly with a change in parameters. We also highlighted results about expressibility. Is one definition a special case or of another definition? In which case, it's very nice because all of the results apply to the special cases. We also try to highlight, these dimensional interaction that we described earlier. Like, this definition is essentially a combination of this simpler one and this other simpler one. This is how we try to bring simplicity to these complicated fields. For each definition, we also listed whether they satisfy privacy axioms, post-processing and convexity, as well as whether it composes. So when you combine two mechanisms that satisfy a definition, do you still get that definition satisfied, possibly with the changing parameters? These properties are what took most work. Drawing links between definitions when the papers didn't do that was really sort of the bulk of this systematization of the knowledge paper. Finally, you have to draw a line somewhere. For example, for composition, we thought, well, it would be nice to, for example, research what is the best composition result out there for a given definition, and try to find this one. Or is this enough to simply say that a composition result exists with some change in parameters, but don't try to over-optimize this? We settled on the latter. Even though the former would also have been useful, we can't do all the things. We also didn't go into too much detail about the context in which definitions are applied, like, for example, contrasting the local versus global model of differential privacy. The second challenge is that the field of differential privacy is quite chaotic and inconsistent. People are using very different notations, redefining things with different names, or defining a completely novel definition using a name that's already taken. We found, for example, 3 definitions that were called Bayesian differential privacy. All 3 have nothing to do with each other. So we think that finding those out, finding information like, oh, this definition that was defined in these 3 papers with 3 different names is actually the same thing, is what convinced us that this was valuable work to do. Hopefully, next time that someone comes up with a new definition ID, they can simply say, look, I'm just combining these 2 existing things. Or I'm using this definition with these specific parameters. Or even better, it turns out that what I need already exists and has been defined elsewhere, so I don't need to define anything new at all. Okay, worse than these problems, some definitions are broken. As in, we send an email to the paper authors to ask for clarifications, because when we look at the definition, it doesn't really make sense to us. And they just tell us, oh yeah, you shouldn't be using this. This definition doesn't make sense. We just didn't realize at the time that paper was published. Papers are sometimes retracted when the results are wrong, but when definitions are kind of meaningless, but all of the theorems and the experiments are technically correct, then the papers are not retracted. So something that maybe everybody in the field knows, that mostly doing that work mostly brings value to newcomers in the field who have no idea that paper is actually doesn't make a lot of sense. These 2 questions at least they get resolved quickly, so this is not the worst. The last 2 categories really gave us a tough time. Some definition provide an intuition for why are we defining these variants that just doesn't match what the definition is actually doing. Some others, they have serious issues, but it's not immediately straightforward, and the authors might disagree and still argue that they're valid, and they might be used in certain cases. These problems are they make these definitions really difficult to classify and to explain, because taking the point of view of we're just going to explain these variants with a completely different intuition than the original paper did might confuse people more than bringing simplicity to the field. So, fun fact on this, we got an entire new paper born out of these discussions about what's the correct way of modeling an attacker without perfect background knowledge. It's harder than it looks. It's harder than it looks. You can hit me up if you want more details after the talk. So, some other more minor challenges. The more you get expertise, the more we've read a bunch of definitions and started drawing links between them, the easier it became for us to do this. So the harder it became to put ourselves in the shoes of someone new to the field. But we're doing that work for them, right? So we're doing that work to try and come up with a really easy intuition to give. But if you understand him because you became an expert in the field, it becomes harder to actually find out the simple explanation that doesn't require all of the knowledge you already know. Another challenge is that papers sometimes strongly disagree with each other about, for example, what's the best way to adapt differential privacy to a setting where you want to take into account data correlations. Placing the arbiter of saying this definition does it this way, this definition does it the other way, and trying to find some reason for this, ending up playing the arbiter is a little bit uncomfortable. Finally, exhaustivity is also difficult. There's never really any way to be sure that we didn't miss something important. So, how well did we do? We hope that we did reasonably well on exhaustivity, and hopefully on simplicity. The dimension model isn't perfect. Sometimes you can kind of combine two definitions in the same dimension, although it rarely makes a lot of sense intuitively. Some combination between dimensions probably would be also awkward, but overall we think it works well. Generally, we found that we could bring a lot of simplicity and explainability to existing definitions using the dimension model. And we produced this ridiculous table, which we sure would have liked to have back when we were both starting our PhDs. Okay. Oh yeah, that was only part of the table. A small part, actually, now that I think of this. Okay, now that's it. This is the table that's in the long version and not in the PETS version because, page limits. Hopefully when that talk is being broadcast at PETS, the long version is going to be available in archive, otherwise probably give us a couple of weeks and we'll get this done. Okay, that's all for me today. Please hit me up with questions, for example on Twitter. This is what it looks like, what it was like to work on this systematization of knowledge paper. We're quite proud of what we accomplished, but it was also more work than I think any of us expected. And I will now take your questions. And I see that I have more time left. So I have one last message for you all. If you're thinking about creating a new variant or a new extension of differential privacy, thanks a lot. I will now take your questions.